All right, we're back. We're on page 2 of notes 4 of Calc C, and we are now talking about series. It's kind of like a reintroduction a little bit. We talked about Taylor polynomials at some point, Maclaurin polynomials. When you took Algebra 2 or pre-calc, you probably did sums of infinite geometric series. And so we're going to talk about those a little. Turns out those are really important, by the way, which is awesome because they're also not super hard to find. So let's see what we got on this page. So I mentioned it last time. So maybe it isn't obvious to you, but if a series only has a finite number of terms, it could be a trillion terms, but a finite number, then it definitely has a sum. You can add up a finite number of things. You just like add the first two, get a number, and then add the next one to that, add the next one to that, and you just keep going, right? So a finite number of terms will definitely have a sum. We're more interested in an infinite number of terms and like what happens then, because things get weirder as you get to infinity or as infinity gets involved. So let's see if we can kind of like investigate this and just see like where some of the problems are going to come from. Not issues, but problems, like the literal problems that you're going to try to solve. Like where are they coming from? So let's see, right out the 13th degree Taylor polynomial of sine of x. All right, so it's centered at 0, so it's actually Maclaurin, and sine is an odd function, so I know that sine of x is approximately, all right, odds x, and then it alternates. I don't know why we're doing 13th, but I don't know. We're almost there. Barely enough time to gripe. It does seem excessive though, but whatever. If I wrote equals, no, approximately, okay. I was gonna be so mad at myself. All right, so there we go. This polynomial, that's Taylor polynomial, is approximately equal to sine of x. First four terms, general term of the infinite series that sums to the sine of 1. All right, so sine of 1 means that I'm going to replace every x that I see up here with a 1. So I'm going to get that the sine of 1 and the general term. All right, so the sine of 1 actually equals, this is not an approximation because we're going forever. So it's going to be 1 minus 1 over 3 factorial plus 1 over 5 factorial minus 1 over 7 factorial. That's 4 non-zero terms plus dot 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 plus the general term, negative 1 to the n. Did I not do the general term last time? I wasn't supposed to. All right. Yep. All right. Negative 1 to the n over quantity 2n plus 1 factorial. So why negative 1 to the n? Well, like the general term is negative 1 to the n x to the 2n plus 1 over the quantity 2n plus 1 factorial. So what we're really doing is this, from 0 to infinity. So this would actually equal sine of x. Like if we went to infinity, we would get that. But so I'm not actually done. I was just explaining where the 1 came from. But here, since we're plugging in 1 for x, we just get negative 1 to the n over that. Plus dot dot dot. Now we're done. Okay, that plus dot 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 is really important because that's what takes you from a finite thing to an infinite thing. If you don't do plus dot dot dot, then you're ending at the nth term, whatever n is. Like maybe n is 2 million, but you're going to end there, right? So you got to do plus dot dot dot. Write a summation with an infinite upper bound that is equal to sine of 1. All right, so I'm going to use this thing that I just wrote here, actually. So I know that the sine of 1 is equal to, go from 0 to infinity, negative 1 to the n. And then it's 1 to the 2n plus 1, but 1 to the 2n plus 1 is just 1 over the quantity 2n plus 1 factorial. So that's actually equal to it. So now what we want to do is see what's happening with the sequence of partial sums. I don't know that this table actually has enough terms for you to see that. So let's find out. So let me go here. And what we're going to do is we're going to look at a sequence of partial sums. So I got to write first, I guess what we're going to do is the sum from n equals 0. So just 0 to 0 first, right? So negative 1 to the n over quantity 2n plus 1 factorial. And it's just 1. And now I'm going to make it easier to do this. I'm going to change this into k, and then at the end do such that k is equal to 1. So it's going to take n equals 0, plug it in, get a value. Take n equals 1, plug it in, get a value, add those together, and be done. So decimals for sure. All right, so we get that. Let's do 2. We do this. I guess I should be writing these in the table. So it was 1, and then it was 0.833. Then it was 0.842. Let's see what happens when we go to the next one. 3.841, let's say. Let's do the next one. 0.841. So it's possible, let's see. So it looks to me like the series is converging to 0.841 something, right? So if we keep going, let's go to like 10. Let's go. So you can see actually the difference between 5 and 10, you can't see. Like there is a difference, but you can't see the difference because already at 6 decimals, you locked in all of those. So it seems to me the sine of 1 in radians, you have to be in radians or this makes no sense. The sine of 1 should be approximately 0.841471. And it is. That's what we're doing. So we created this sequence of partial sums, and the partial sums were approaching a value. The value they're approaching is the sine of 1. So this is showing us that the series converges to this decimal, which turns out to be exactly the sine of 1. If we had an infinite number of terms for that decimal. I mean, that's an irrational number, which is another weird thing. Like series generate irrationals like crazy. Like you can write all kinds of irrational things using series, which I've always thought is kind of weird. So it looks like the limit as n approaches infinity of s sub n, our nth partial sum, is just the sine of 1. And we saw that that's approximately 0.0841. And so we get that. So we look at the partial sums. While we're here, I'm just going to do these. So find the exact value of each of the following through recognition. So this is the thing that I did on the previous page with the e to the x over 2. You look at the denominator, and you see a 2n plus 1, right? So 2n plus 1 should go with sine. 2n plus 1 factorial should be sine. Right, but it's sine of what? So start rewriting. So try to get everything you can to be to the 2n plus 1 factorial, 2n plus 1 power. Maybe 1 to the n. Then I got a pi over 6 to the 2n plus 1 over 2n plus 1 factorial. All right, as soon as I write it like that, this should be equal to the sine of pi over 6, and the sine of pi over 6 is 1/2. This is a crazy, insane way of writing 1/2. But that should be what it is. We can check it on the calculator. I mean, it's definitely right. But all right, so the next one, I look at the denominator. I see 2n factorial. And I remember that 2n factorial is in the denominator of cosine. So I'm thinking this is the cosine of something. So I need to focus in, though, on these 2n's, right? 2n, 2n, 2n. There's an extra 3 in the denominator. So maybe my first step would be this. Negative 1 to the n, quantity 4 pi to the 2n. 3 times 3 to the 2n, 2n factorial. Okay, one of the properties of summations is you can factor out constant multiples. That's like a property of everything, basically, so that constant multiples can come out. We get this. Now let's put things with the same exponent under the same set of parentheses, right? So they live in the same house. 4 pi over 3 to the 2n, quantity 2n factorial. Okay, so this should be 1/3 the cosine of 4 pi over 3. Okay, cosine of 4 pi over 3 is negative 1/2, so this should be negative 1/6, I think. Let's see if the calculator can do them. So sometimes it can, sometimes it can't. It just depends on how complicated it is. I, however, am confident. So if it can't do it, what I'm going to do instead is I'm just going to do like a very large partial sum and see. But I think it's going to do it. infinity. So infinity is in the pi key. Use the pi key a couple times and it'll give you that. Touch the pi key a couple times is what I was going to say. That's weird. Pi to the 2n plus 1, 6 to the 2n plus 1, quantity 2n plus 1, factorial. No dice. No dice on that one. All right, so what can we do? Let's do 100. Let's do 1,000. I always get in trouble because I try to go too big. What is this warning? Oh, overflow replaced with infinity or negative infinity. So it knows that it's 0.5, but it won't give you the exact value of 0.5. That's really interesting to me. What if, so it's like now it becomes this game where I'm like, can I get it to, like, I know you know it. Can you just tell me? Nope, can't do it. Weird. All right, let's see if the other one works. I think it probably won't based on this. Let's see. So from 0 to infinity of -1 to the n 4 pi to the 2. Oh, I had another thought on that last one. Well, we'll see how this goes. 2n plus 1. This one's trickier though, so I expect this to work even less than the last one. Yeah, it's not happening for us. Let's change this to 100 and get a decimal. Do -1/6. So we got it. Calculator won't do it. What if I change this to, I'm gonna go back to this one because it's a little simpler and just change this to X. Do you know what this is? No, why not? Why do you not know that? I don't know. I don't know why it's not doing it, but whatever. We definitely got it right. Numerical analysis turns out to be incredibly useful when you're doing these things. So, I mean, the calculator knows how to do it, but it doesn't necessarily have the ability to do it, if that makes any sense, which it maybe doesn't. All right, but we got them, and we were able to check it because we looked at the 100th partial sum. It's really the 101st partial sum, but don't worry about that. And we saw numerically, they're definitely the values that we got. But we were able to do it because sometimes we're a little better at these things than the calculator. We're able to think a little more dynamically than the calculator can think about these things. But anyway, good intro to some stuff. I'll be back in the next one and do some more. So I will see you there.